Hello friends, in this video I'd like to solve the following problem from the Indian Mathematical Olympiad 2005, problem number 3. We wish to find all functions f from the set of real numbers into itself, satisfying the following equation. F of x squared plus y f of x equals x times f of x plus y for all real numbers x and y. It's a beautiful functional equation from India, but it is a bit complicated, so stick with me. I will start with giving you some hints. My hints for this problem are the following. First, set y to be 0. Set y to be 0 to find f of 0. Then rewrite our equation changing y to y minus x. And then you should consider two cases. First case, supposing that f of x0 is 0 for some non-zero argument, show that then our function must be constantly 0. And furthermore, supposing that f is not constantly 0, show that our function must be in fact surjective. And now, the complicated part, you should show the following. Supposing that for some non-zero argument x, the value of our function is not 1, show that we can set this argument x to be x times f of x minus x squared over f of x minus 1. Set this argument to show that our function is either x or x is 1, which is a very powerful condition already. And finally, show that f of x cannot be 1 for arguments which are not equal 1 by supposing to the contrary that it can, and use the fact which was established previously, and the fact that f of x squared equals x times f of x, which was established in the beginning. So give this problem a try, and I will see you in just a minute. Alright, so let's start. Let's start with setting by calling our equation asterisk, and let's set y to be 0. Y to be 0 in our condition asterisk. Then we will have the following, very important, so I will write it in yellow. F of x squared equals x times f of x. And I will call this condition triangle. Right. In particular, setting x to be 0 in our condition triangle, then we have that f of 0 is 0. It's also important, we'll use it later. And now let's change y to y minus x in our very first functional equation asterisk. Then we will have the following. Our equation can be rewritten in the following way. F of x squared plus y minus x f of x equals x times f of y. And now I wish to consider two cases. Case number one. Well, f of some non-zero number is 0, or some x0 not equal 0. Notice that then the line written above, I will call it double asterisk, then double asterisk becomes the following. On the left hand side we have f of x0 squared, or maybe let's write it explicitly, that then set x to be x0 in our condition double asterisk, and we will have the following. F of x0 squared equals x0 f of y, because this part vanishes, which means that f of y equals f of x0 squared over x0, but this is just a constant. Yes? So our function is constant, and let's do verification. Or let's write, so f of y equals c for some constant c. And let's do verification. Verification is very quick. Verification. Our equation, which I marked double asterisk, well, on the left-hand side of this equation, we have just c, and here we have c times x. And that should be true for every real number x, which can only mean that c equals 0. And in fact, this function satisfies our equation. So we have just one solution, a solution. We have already established one solution, function which is constantly 0. So that was quick. So let's now consider case number 2. Case number 2, that function f is not constantly 0. Is not constantly 0, or rather we can write even stronger that f of x is not 0 for any non-zero argument, because we have demonstrated that if f of x is 0 for some non-zero argument, then our function must be constantly 0. Then we have the following. We will consider once again our equation double asterisk, and I will set, for example, x to be 1. I will set x to be 1. Or, no, sorry, I will set y to be 1. So set, for example, y to be 1 in our condition double asterisk. Then we see the following. We have f of x squared plus 1 minus x times f of x equals x times f of 1, and notice that f of 1 is not 0, so the function on the right hand side, this function is surjective. So the function f standing outside on the left hand side must also be surjective. Maybe let's write it in a different color. F is surjective. I will call this condition by inverted triangle. All right. Now the nice part. Suppose now that we have some non-zero real number x, and that f of x is not equal 1 for this argument. And consider set y to be equal to the following: x times f of x minus x squared over f of x minus 1. Let's set this in our condition asterisk, or double asterisk. What a strange argument, you may say. Let's also recall our condition double asterisk, which says that f of x squared plus y minus x times f of x equals x times f of y. Now, why have I chosen this very argument? Well, you can verify it easily that it makes this argument right here equal to y. Let's verify it. Notice that x squared plus y minus x times f of x. For this argument y, it can be written as x squared plus x f of x minus x squared f of x minus 1 minus x times f of x. Well, it can be rewritten in the following way. X squared, let's make a common denominator. We have x squared f of x minus 1 plus x f of x squared minus x squared f of x minus x f of x squared plus x times f of x. And we have a bunch of cancellations going on, namely this cancels with that, and moreover here we have x squared f of x. This part cancels with this part, and we are left with just x times f of x minus x squared over f of x minus 1, which equals, very importantly, it equals y. This equals y for this choosing of argument y. Our equation double asterisk becomes, on the left hand side we have f of y, and on the right hand side we have, or maybe let's replace y by this argument. So it's f of x times f of x minus x squared over f of x minus 1 equals x times the very same thing. And for that to be true, we have two options. Either this equals that equals 0, or x equals 1. So we see that either x equals 1 or, well, f of x times f of x minus x squared over f of x minus 1 equals 0. But remember that we are supposing that for every non-zero argument, the value of our function is not 0. So the second option implies in turn that x times f of x equals x squared. But remember that we have supposed that x is not 1, is not 0, rather, x is not 0. So we can safely divide by x, and we get f of x equals x. Very important. Let's write our result in a compact way. We have established the following fact, that for every non-zero number x, if f of x is not 1, then either x is 1 or f of x is x. Or, using basic laws of logic, or equivalently, for every non-zero real number and not equal to 1, either f of x is 1 or f of x is x. For every non-zero and not equal to 1 number x, either f of x is 1, or if it's not, then f of x is x. It's a very powerful condition because it says a lot about our function. Very, very much. And let's call this condition square. And now what I wish to do is to eliminate this first possibility. I will show that it's not possible for our function to be 1. So suppose now that f of x equals 1 for some real number x which is not 0 it is not 1. Alright, we have established a minute ago, or a couple of minutes ago, this fact right here, which I marked by yellow triangle, that f of x squared equals x times f of x, and now it's time to use it. So by our condition triangle, f of x squared equals x times f of x equals x, because f of x, I'm supposing that it is 1, and it's not 1. So by our condition square, since it's not 1, it must be x. By our condition square, well, f of x squared must be equal x squared. It can't be 1. We have demonstrated that it can't be. So we have the following problematic equation: x squared equals x, which is contrary to the supposition that our number is neither 0 nor 1. Contradiction. It's a contradiction, which means that our condition, which I marked square, can be written in a strengthened way. We have demonstrated that for every real number x which is not 0 and which is not 1, f of x is x. Well, and what about 0 and what about 1? Because it's almost the identity function. Well, we have established also that f of 0 is 0. And notice that since f of x is not 1 for x's which are different than 1, it follows from this condition. And since our function is surjective, and since f is surjective, it must be the case that f of 1 is 1. Yes, because 1 has to be attained somewhere. It cannot be attained at any other argument than 1, so it must be attained at 1. So, which means that in fact for every real number x, f of x is x. And let's do verification. Verification is very easy. Verification. I need a new page. Verification of our equality. Let's do verification. On the left-hand side, in our original equation, we have f of x squared plus y times f of x, which equals, well, x squared plus yx. And on the right hand, which can be written as x times x plus y which is x, f of x plus y, which is exactly on the right hand side. So it is verified. So we have exactly two solutions. These solutions of our equation are exactly two. Either f is a zero function or f is the identity of a set of real numbers. And that closes our problem. That closes our solution. A very nice problem, I'd say. It was very creative. The crucial step, if you think about it, the crucial property was property which I marked by square, and it followed from this choosing of argument y. This crucial choosing of argument y, that y equals x f of x minus x squared over f of x minus 1. It was the crucial step. And also I will reiterate it once again that I have chosen this argument because of the following fact that x squared plus y minus x times f of x equals y for this choosing of argument, which simplifies our functional equation to this form. Alright, very nice problem. Once again, two solutions, zero function and the identity function. So thank you very much for watching. I hope that you've learned something new this time, that you are entertained. And yes, I will see you next time. Have a nice day. Goodbye.